Hello everyone, my name is Aryan and today I will discuss Fisher Neymann Factorization Theorem. Okay, so as in my last lecture I have discussed about sufficiency and I have already mentioned there how to check the given estimator is sufficient or not by conditional distribution approach. Okay, so today I will discuss one more theorem is known as Fisher's Neymann Factorization Theorem. Okay, so first question is that what is factorization theorem? Okay, so now you can see here factorization theorem provides the necessary and sufficient condition for a distribution to admit sufficient statistics. Okay, that means factorization theorem provides necessary and sufficient condition for a particular distribution or for a given distribution to admit sufficient statistic. Okay, is it clear? So this is the main factorization theorem statement, but how we can define it? So now you can see here statement part. Okay, so let capital X be a random variable with density fx theta for theta belongs to parameter space and a statistic capital T and T is function of x1 x2 xn is sufficient estimator of parameter theta if and only if the joint density function capital L can be expressed in the form of capital L is equal to z t comma theta into hx. Okay, that means if t is sufficient estimator for parameter theta, then likelihood function can be expressed in form of gt comma theta into hx. Okay, so now you can see here what is gt comma theta and what is hx here. So where zt comma theta depends on theta that means parameter and x only through the value of t of x is equal to capital T. That means capital T is what? Capital T is function of x1 x2 xn. So here x only through the value of capital T. Is it clear? That means here in gt comma theta t is capital T and theta is parameter. Okay, and second term is hx. So hx is what? Hx is a function of x only and independent of parameter theta. Is it clear? So if likelihood function can be expressed in terms of zt comma theta and hx, that means we can conclude that a statistics is sufficient estimator for parameter theta. Okay, okay, so this is the statement part. Okay, so today I am not going to discuss about the proof part of this statement. So now come to the one problem to check how you can utilize this factorization theorem to particular problem. Okay, so just you can see here I have mentioned here one problem. Let x1, x2, xn be a random sample from normal population with mean mu and variance sigma square. Find sufficient estimator for mu and sigma square. Okay, that means question is find sufficient estimator for mu and sigma square. So come to the solution part. What is given that? Given that x1, x2, xn follow normal mu comma sigma square. Okay, and we can let theta is equal to mu comma sigma square. Okay, because here we have two parameter mu comma sigma square, so theta is mu comma sigma square. Okay, so come to the next step. Okay, so we know that probability density function of normal distribution is 1 upon sigma root 2 pi exponential minus half x minus mu upon sigma square. Okay, and range of x, mu and sigma square is given here. Okay, so by factorization theorem or using factorization theorem, firstly define the likelihood function of x1, x2, xn. So by definition we can write it likelihood function capital L is equal to product of f theta xi. Okay, so what is the value of f theta xi? Value of f theta xi is this one. Okay, this one. So now put the value of f theta xi, and now you can see here capital L is equal to product I going from 1 to n 1 upon sigma root 2 pi exponential minus half xi minus mu upon sigma square. Okay, so simplify this term. Just take first term n times, that means 1 upon sigma root 2 pi to power n, and second term is exponential, and we are taking n times of this term, so it becomes exponential summation. Okay, so exponential minus 1 upon 2 sigma square and summation I going from 1 to n xi minus mu whole square. Is it clear? So as I have already mentioned in last lecture, how you can write product exponential in form of the summation. Okay, so now come to the next step. Just simplify this step in form of next step. You can see here first term I have mentioned here as it is, and second term what I am doing here, exponential minus 1 upon 2 sigma square, just expanding xi minus mu ka whole square, that means a minus b ka square. So I going from 1 to n xi square plus mu square minus 2 mu times xi. Okay, is it clear? Then in next step just take summation sign inside, and we get, now you can see here 1 upon sigma root 2 pi power n exponential minus 1 upon 2 sigma square. First term is summation xi square, second term is summation mu square. Mu is constant, so it's become n mu square. Okay, and last term is minus 2 mu constant, and I going from 1 to n xi. Is it clear? So now you can see here likelihood function is equal to zt comma theta into hx. Okay, that means this whole function is function of mu and sigma, and you can see here we have two function of xi's. One is this function and one is this function. Okay, so that means this is dt comma theta, and hx is what? Hx is 1 here. So now you can write it L is equal to gt comma theta into hx, and where gt comma theta is equal to first term is 1 upon sigma root 2 pi to power n exponential minus 1 upon 2 sigma square, and we are considering here summation of xi square is equal to t2x. Okay, and then taking third term here minus 2 mu, and summation of xi is t1x plus second term plus n mu square. Is it clear? Okay, so now you can see here tx is what? T1x and T2x, and T1x we have considered here. T1x is summation of xi and T2x is summation of xi square, and hx is 1. That means summation of xi is associated with mu. You can see here. Okay, and summation of xi square is associated with sigma square. That means T1x is equal to summation of xi is sufficient for mu, and T2x is equal to summation of xi square is sufficient for sigma square by Neymann Factorization Theorem. Okay, is it clear? Okay, so for more clarification, I have considered one more problem for the discrete random variable. So now you can see here, I have mentioned one more problem here, and problem is if x1, x2, xn are independent and follows Bernoulli distribution with parameter theta, examine whether t is equal to summation of xi is the sufficient estimator for theta. Okay, I have already explained the solution of this question in previous lecture, where I have mentioned conditional distribution approach. So you can you have two methods. Either you can check this resultant by conditional distribution approach, otherwise you can use Fisher's factorization theorem. Okay, so now we are using here factorization theorem. So now you can see here solution part. Probability mass function of Bernoulli distribution with parameter theta is this one, theta to power x 1 minus theta to power 1 minus x. Okay, where x takes value 0 and 1. Now by factorization theorem, define likelihood function. Likelihood function is joint density, means P of x1, x2, xn. Okay, and x1, x2, xn all are independent in questions already mentioned here. Okay, now you can see here, so all are independent, then you can write it probability of x1 into probability of x2 into probability of xn. Okay, and we know that this value, and this value, to put the value of probability of x1, probability of x2, probability of xn, we get this expression: theta to power x1 1 minus theta to power 1 minus x1, theta to power x2 1 minus theta to power 1 minus x2, and so on, theta to power xn 1 minus theta to power 1 minus xn. Okay, so simplify this expression. Okay, so this becomes theta to power x1, theta to power x2, and theta to power xn. So first term becomes theta to power x1 plus x2 plus and so on plus x. Okay, similarly combine 1 minus theta term. So now you can see here 1 minus theta power 1 minus x1, 1 minus theta power 1 minus x2. Okay, similarly 1 minus theta power 1 minus xn. So base is common, then power again becomes 1 1 1 n times, so it's become 1 n. Okay, it's become n minus x1 plus x2 plus and so on xn. Okay, so now you can write it likelihood function L is equal to x1 plus x2 plus xn is what? Summation of xi. So this is theta to power x summation of xi, and 1 minus theta to power first term is power n, and minus x1 plus x2 plus xn is what? Summation of xi. Is it clear? So now you can see here in whole term what we have: parameter and function of xi's. Okay, so that means which is the form of z t comma theta into hx, where z t comma theta is whole quantity and hx is what? Hx is 1. Okay, is it clear? So now we can conclude that hence by factorization theorem, t is equal to summation of xi is the sufficient estimator for theta. Okay, so this is the second way by factorization theorem you can verify that given estimator is sufficient or not. Okay, so thank you so much to everyone for watching this video, and again we will meet with next problem and solution. So for today, thank you.